Welcome to Generative AI Futures, brought to you by ByteGoose AI. So for the last, several years now, it feels like the whole story of AI progress has boiled down to one word: scale. We've been living in this era, the big model era, where the common wisdom was just bigger is better, always.
Absolutely. If you wanted smarter AI, the answer was always more parameters, load up on more data, and, well, you needed way more compute power. Simple as that.
But that era, it feels like it's being seriously challenged now, doesn't it?
Oh, fundamentally, yeah. There's this really powerful counter movement picking up steam, and it's making everyone rethink efficiency. The new frontier isn't just about building these, enormous one-size-fits-all large language models, LLMs.
Right.
It's really about taking small language models, SLMs, and figuring out how to make them incredibly smart, but also incredibly efficient.
And I think what's really key for you listening is that this isn't just some academic debate about, being green or saving costs, although that's part of it.
Sure.
We're actually looking at three specific, really cutting-edge technical strategies. These are based on 3 recent publications, and they basically prove that capability is starting to decouple from just sheer size.
That's the core of it. Our mission in this deep dive is really to get into these 3 different paths engineers are carving out. They're unlocking these really high-end abilities, not by just adding more layers or parameters, but by being fundamentally, cleverer, smarter in the design, the training, the whole architecture.
It's kind of like a new playbook for AI power, isn't it?
Exactly. A new playbook.
So we've got 3 routes we're going to cover today. First up is what we're calling system-level innovation. This is all about how you use SLMs as these little specialists inside bigger, smarter agentic systems, sort of distributing the intelligence. Then second, we'll dive into training methodology innovation. This focuses on something called prolonged reinforcement learning, or ProRL. The idea here is you can unlock totally new reasoning powers through really intense, long-haul training.
Yeah, pushing the training much further than usual.
And finally, the third path, architectural innovation. This is where things get maybe the most radical with tiny recursive models, TRMs. These models use this kind of deep, iterative thinking process, almost like looping back on themselves, to solve these really hard logical puzzles that just completely stump the giant models.
Yeah, models that are literally like a million times bigger in terms of parameters. It's quite something. This is the roadmap to power through precision, not just brute force.
Okay, let's unpack this first pass then. Using SLMs in these agentic systems, I think we really need to nail down the definitions first, because the whole economic case, the operational argument, it all hinges on understanding the difference between these heavyweight generalist models and the nimble specialists.
That distinction is absolutely crucial. Yeah, so when we say large language models, LLMs, we're talking about the big beasts, right? The ones that absolutely need huge cloud infrastructure, massive data centers. I think, tens of billions of parameters, minimum going up into the hundreds of billions, like your 70B models, your 175B class models. The giants. They're the generalists. They're built to be these foundational, all-purpose conversational partners, kind of like walking encyclopedias.
And then the small language models, SLMs, these are typically defined how? Below 10 billion parameters.
Generally, yeah. Under 10 billion parameters is a common threshold. And the critical thing about that size is it's what allows a model to actually run effectively on, normal consumer hardware. Laptops, maybe even powerful phones, edge servers.
Right. So you can get inference done locally with low latency for maybe one person or a small group.
Exactly. That's the key differentiator. They have the potential to be the specialists running closer to where they're needed.
Okay, so we have LLMs, the big generalists, and SLMs, the smaller potential specialists. Now, layer on top of that this idea of agentic AI. What does that mean in this context?
So agentic AI is really the application layer here. Think of agentic systems as being designed as doers. They're not necessarily built for, deep, nuanced human conversation across any topic. Their job is usually to break down some big, high-level goal into a series of smaller, more manageable steps.
Okay.
These steps are often repetitive, specialized subtasks. Things like figuring out the user's intent from a short command, or classifying the sentiment of a customer review, or pulling specific bits of data out of a structured document, maybe calling an external tool or an API. That kind of thing.
Got it. And this is where the big economic argument for using SLMs really clicks into place, isn't it? Because using one of these massive, 175 billion parameter models for those kinds of narrow, repetitive tasks.
It's total overkill.
Yeah.
As the research puts it, it's like using a sledgehammer to crack a nut. or maybe a cruise missile to open a can of sardines, as you said earlier.
Right. You just don't need that vast general knowledge and conversational ability just to, say, parse a very specific API request format or summarize a 5-line error message.
Exactly. And the operational reasons, the practicalities, they become really hard to ignore. Just think about the cost of running the model, the inference efficiency.
Okay.
Serving a 7 billion parameter SLM, the data shows it's somewhere between 10 and 30 times cheaper than serving a big 70B or 175B LLM.
And cheaper across the board. You mean latency, energy?
Across the board. Lower latency, much lower energy consumption, and fewer raw computational FLOPs needed per request.
Right.
It's a massive difference.
That cost factor, I mean, for any company running applications at scale, that's not just interesting, is it? If you have an agent system making millions of these specialized calls every day.
That 10x, maybe 30x cost saving, it goes from being a neat research finding to basically a mandatory business strategy if you
Right.
want real-time responses that can actually scale affordably.
And it's not just the running costs, right? The research talks about agility, too.
Oh, huge factor. Agility. Think about needing to update the agent. Maybe you need to add a new specific behavior, maybe handle a new product type, or maybe you find a bug in how it processes, say, financial data formats.
Yeah.
With an SLM, because it's small and specialized, you can often fine-tune it, update it, and redeploy it potentially overnight.
Overnight, how does that work? Because fine-tuning one of the giant LLMs sounds like a massive, weeks-long project.
It often is for the big ones. But for SLMs, we can use techniques called parameter-efficient fine-tuning, or PEFT. You probably heard of things like LoRi, low-rank adaptation, or QLoRi, which is a quantized version.
Right, LoRa and QLoRa.
These methods let you inject new specialized knowledge or behaviors by only training a tiny, tiny fraction of the model's total parameters, sometimes just a few hours on a single GPU.
Wow.
So yeah, adding new skills, fixing specific issues, it becomes incredibly fast. Businesses can iterate much quicker, maybe respond to new compliance rules almost immediately.
Which is a world away from the monolithic LLMs where, like you said, a big retraining or deep fine-tuning cycle can take weeks or months and needs computing resources that only a few giant tech companies actually have.
Exactly. So that agility factor alone means these SLM-based agent systems can adapt to market shifts or new requirements in ways that the big, slow-moving LLM systems they just can't keep up.
And there's another angle, too, isn't there? Deployment flexibility.
Absolutely. Because they're small,
Yep.
SLMs are perfect for edge deployment. You can run them directly on a user's laptop or on a smartphone, or maybe on specialized hardware right there on site in a factory or a hospital.
And that gives you, what, offline capability.
Offline capability,
Yeah.
definitely. Much lower latency because you're not doing that round trip to a distant cloud server. And really importantly, for many industries, much better control over your data.
Privacy and security.
Exactly. If you're in banking or healthcare or defense, keeping sensitive data localized and under your control is often non-negotiable. SLMs make that feasible.
So the big picture, the architectural vision that's emerging here, it's not about getting rid of LLMs entirely, is it? It's more like a hybrid system.
That's the term the researchers often use. Heterogeneous systems. Yeah. The intelligence isn't all packed into one giant brain anymore. It's distributed. The default approach becomes SLM first.
SLM first, okay.
Think of the SLMs as your specialized frontline workers. They're fast, they're precise within their domain, and they're cheap to run. So they handle the vast majority of the workload, maybe 99% of all the common recurring requests.
And the big LLM, what's its role?
The LLM becomes the expensive consultant, the specialist you call in only when you absolutely need that broad general reasoning power, maybe for really high-level strategic planning or handling a truly complex, open-ended conversation that's way outside any SLM specialty, or maybe figuring out a novel multi-step plan that requires synthesizing lots of different information.
So you use the LLM sparingly, selectively, only when its unique general capabilities are the only tool for the job.
Precisely. And there's solid evidence backing this up, challenging that old scale is everything belief. The paper mentions Toolformer, for instance.
Right, Toolformer, that was just 6.7 billion parameters.
Yeah, tiny compared to GPT-3 at 175 billion. But Toolformer was shown to beat GPT-3 on specific tasks involving using external tools or APIs. Why? Because it was specialized for exactly that function.
And there are newer examples too, right? Like DeepSeek R1 Distill.
Exactly. That's a 7B model, and it demonstrated performance on certain specific reasoning tasks that actually surpassed some of the huge proprietary models like Claude 3.5 and even GPT-4.
So the intelligence isn't just in the model itself, but in the whole system's design. the ability to pick the right specialist for the right task.
That's the key takeaway for this first path. It's about efficiency and power through smart system design and orchestration.
Okay, that makes a really strong case for the system-level approach. Using SLMs as agents makes a lot of sense economically and operationally, but like you said, it still kind of relies on having that LLM level knowledge available somewhere, even if it's used sparingly. So for this second path, ProRL, we're asking a different, maybe deeper question. Can we actually make a small model fundamentally smarter, more capable on its own, not just organize it better within a system?
Exactly. Now we shift gears to training methodology innovation with prolonged reinforcement learning, ProRL. And this gets right into a pretty significant debate within the AI research community about what reinforcement learning, RL, actually does to a language model.
Okay, let's clarify that debate. What's the core question?
The fundamental question is, does RL truly expand what a model knows or how it can reason? Does it teach it genuinely new skills? Or does it just make the model better at finding and sampling solutions that were kind of already hidden or implied within its original pre-training data?
So is it creating new knowledge or just optimizing access to existing knowledge?
That's the crux of it.
Mhm.
And a lot of earlier studies seem to lean towards the latter, that RL was mostly a refinement step,
Mhm.
optimizing how the model used what it already implicitly knew, rather than expanding its capabilities in a fundamental way.
And the ProRL research challenges that conclusion.
Directly, yeah.
Yeah.
The pro-RL paper argues that those earlier conclusions might have been flawed because they basically stopped the RL training too soon. Most standard RL fine-tuning setups for language models only run for maybe a few hundred training steps.
Okay, only hundreds of steps. And ProRL, how long are we talking?
They designed their system to be stable enough to train for over 2,000 steps, a significantly longer horizon.
2,000 steps. Okay, that's a huge difference. How did they manage that? Keeping RL stable for that long sounds like a nightmare.
It required some major technical innovations, starting right at the core algorithm. They actually ditched the standard algorithm, proximal policy optimization, or PPO, which is almost ubiquitous in RL for LLMs.
They ditched PPO. Wow. Okay, what did they replace it with and why? PPO is usually seen as the go-to for stability.
They adopted something called Group Relative Policy Optimization, or GRPO.
GRPO. Okay, unpack that for us. How is GRPO different from PPO, especially in terms of engineering and stability for these super long runs?
The main advantage of GRPO in this specific context, long training runs, comes down to efficiency and maybe even better stability. See, PPO usually requires a separate critic model. Often, another neural network whose whole job is to estimate how good the current policy is, the value of being in a certain state.
Right, the critic network.
That critic adds computational overhead, it needs to be trained itself, and if it's not trained well, it can actually become a source of instability for the main policy model.
So GRPO gets rid of the critic.
Exactly. GRPO skips the critic entirely. Instead, it estimates the advantage, basically, how much better a particular sequence of actions or trajectory was compared to the average using a relative baseline. It looks at the reward achieved by the current trajectory and compares it to the average reward, let's call it another, of all the other sampled responses within that same training batch.
Ah, so it's comparing within the group.
Right. Normalized by the standard deviation of those group scores. So the model is essentially trained to perform better than its peers sampled at the same time. It avoids relying on that potentially complex and unstable external value estimate from a critic.
That sounds cleaner, theoretically, but still, training for 2,000 steps.
Yeah.
There must have been other stability hurdles they had to overcome.
Oh, absolutely. The paper details 3 really critical technical fixes needed to make this long-term training work without the model just collapsing. The first big one is something called entropy collapse.
Entropy collapse. Okay, for listeners who aren't deep in RL theory, what does that actually look like when it happens to a language model during training?
It's pretty disastrous, actually. It's when the model's outputs become way too similar, too narrow, very early in the training process. Imagine like a person who gets stuck saying the same 5 phrases over and over again, no matter the question.
Okay, it loses diversity.
Exactly. The model loses its ability to explore different possible solutions or reasoning paths. It just keeps generating slight variations of things it already knows, which might not even be good solutions. Policy updates then just stall because there's no novelty, no variety in the outputs for the model to learn from.
So if it locks onto a narrow set of answers too early, it never gets a chance to discover those genuinely new, maybe better reasoning strategies they were looking for.
Precisely. So how did they fight this? They used a combination of engineered randomness and clever filtering. First, During the sampling phase, where the model generates potential answers, they cranked up the temperature specifically to 1.2.
High temperature means more randomness in token selection.
Yeah, encourages exploring less probable but potentially interesting token sequences. But the real key mechanism came from borrowing ideas from another algorithm called DPO, dynamic sampling policy optimization.
DAPO, wasn't that the one with the asymmetric clipping?
That's the one. DAPO helps fight this mode collapse by using different clipping boundaries in the PPO-like objective. They kept a standard lower bound clip, epsilon low 0.22, but used a higher upper bound, epsilon high equals 0.44.
Higher upper bound?
Yeah.
What does that asymmetry achieve?
It encourages what they call clip higher actions. It basically gives a stronger push to increase the probability of tokens or sequences that were initially unlikely but turned out to lead to surprisingly high rewards.
So you're actively encouraging the model to take more risks, to jump into territory it might have initially avoided, but that could pay off big time.
Exactly, pushing exploration. And DAD also uses dynamic sampling. It filters out training examples that are either too easy, where the model already gets it right 100% of the time, or too hard, where it gets it wrong 100% of the time.
Why filter those out?
Because they don't provide much useful learning signal. You want the model to focus its effort on the problems that are right at the edge of its current ability, the intermediate difficulty ones. That's where the most learning happens. Filtering prevents wasting computation on already solved problems or seemingly impossible ones.
Okay, so high temperature, asymmetric clipping, dynamic sampling. That's a lot to fight entropy collapse. But even with all that, over 2,000 steps, the policy could still just drift off into some weird, unstable part of the solution space, couldn't it? This usually requires some kind of anchor.
You're right. And that brings us to the second major mitigation, KL divergence control.
The KL penalty. The classic regularizer.
Exactly. They added a KL divergence penalty to their main objective function. The equation looks something like LKL or theta geta DOPO. Okay, let's break that down. Lol GRPO is the main reward-seeking part from the group relative policy optimization. And the second term, DALP, that's the Kullback-Leibler divergence. Right. It measures how much the current policy, which is constantly being updated, is drifting away from some fixed stable reference policy. The beta term controls how strong this penalty is.
So this KL term acts like a tether, right? It keeps the learning policy from straying too far, too fast from a known stable point.
Exactly. It's crucial for stability over thousands of steps. But there's a catch.
There always is. What's the catch with the KL penalty?
If you keep that penalty active for the entire 2,000-step training run, eventually starts to dominate the loss landscape. The tether becomes too tight. The model gets pulled so strongly towards the reference policy that it just stops improving. It hits an asymptote and can't explore further.
It chokes off the very exploration you need for finding novel solutions.
Precisely. And this is where their third really clever trick comes in. Reference policy reset.
Okay, reference policy reset. What does that involve?
To stop that KL term from becoming a stranglehold, they periodically just set the reference policy. They take a recent snapshot of the current, improved policy TLA, and make that the new stable reference point.
So you let the model strain against the tether, improve significantly, and then just before the tether stops it completely, you move the anchor point forward to where the model has reached.
Exactly. And crucially, when they reset the reference policy, they also reinitialize the optimizer states like Adams' momentum terms. This allows the policy to effectively forget the pull of the old reference and start exploring aggressively again from the new, improved starting point.
That's a really smart piece of engineering. It allows for continuous improvement, continuous divergence into new territory, while still getting the stability benefits from the KL regularization between resets.
It's a cycle of stable learning, followed by resetting and renewed exploration. And this whole combination, GRPO, entropy control, KL penalty with resets, allowed them to train the Nemotron Research Reasoning Q 1.5B model. Okay, so a 1.5 billion parameter model. That's definitely in the SLM category. What kind of data did they train it on with this ProRL method?
A pretty diverse set. About 136,000 problems covering math, coding, general STEM questions, logic puzzles, instruction following. Quite broad.
And the results. Did this intense training actually pay off, especially compared to larger models?
The results were pretty striking. First, the jump in performance over its own base model, the model before ProRL, was huge. On logic puzzles, for instance, the average pass at one rate, meaning getting it right on the first try, improved by nearly 55%. On STEM reasoning, it was about a 25% jump.
Wow, significant gains just from the training method.
Yeah. And it wasn't just better than its base self. This 1.5B ProRL model actually matched, or in some cases surpassed, the performance of the much larger DeepSeek R17B model across a range of benchmarks.
A 1.5B model matching a 7B model, that definitely supports the smarter training beats bigger size idea. It does. But the really convincing evidence, the thing that addresses that core debate about whether RL expands capability or just optimizes sampling,
Yeah.
that came from looking at specific types of problems.
Which types?
They found the biggest gains from ProRL happened precisely on the problems where the base model initially struggled the most. There was a negative correlation between the base model's performance and how much improvement ProRL provided.
Okay, so it helped most where the model was weakest. That suggests it's adding something new.
Exactly. And the smoking gun was the performance on what they called out-of-domain, or OD, tasks.
Yeah.
They identify some really specific novel puzzles, like one called BoxNet.
FoxNet, okay.
On these BoxNet tasks, the original base 1.5B model before ProRL scored 0%, a flat 0 success rate. No matter how many times they tried to sample an answer from it, it just could not solve the puzzle. The necessary reasoning was completely absent, not just hidden.
0%. Okay, that's unambiguous failure. And after ProRL training,
The same tiny 1.5B model achieved a 80% pass rate on some of those specific BoxNet tasks.
0 to 100, okay, yeah.
Yeah.
That's undeniable proof, isn't it? That ProRL didn't just optimize, it genuinely expanded the model's reasoning boundary. It created new knowledge, new internal reasoning abilities that simply weren't there before.
It's about as clear-cut evidence as you can get in this field. And they even backed it up further by using a metric called the Creativity Index.
The creativity index, how does that work?
It basically measures how different the reasoning steps generated by the model are compared to the reasoning steps found in its original pre-training data. Higher scores mean more novel reasoning patterns,
And the ProRL model scored higher.
significantly higher after the prolonged training. It confirmed that the model was generating genuinely new ways of thinking, going beyond just regurgitating or slightly modifying patterns it had seen during pre-training.
Okay, so ProRL is a powerful demonstration of how intensive, cleverly stabilized training can fundamentally boost the capability of even a small model. Path 1 was smart systems with agentic SLMs optimizing application. Path 2 is smart training with ProRL expanding capability. Now let's get into the third path, which you hinted might be the most radical. This is about changing the model's internal architecture itself, the tiny recursive model, or TRM.
Right. This architectural approach is really fascinating because it tackles head-on what might be the biggest weakness of all the standard, large, autoregressive language models: their sequential nature.
Explain that weakness, the sequential token generation.
Yeah. Think about how an LLM usually generates an answer, especially a complex one involving reasoning, like a chain of thought.
Right.
It generates one token, then the next based on the previous ones, then the next, and so on, in a strict sequence.
Auto-regressively.
Exactly. The problem is, if it makes just one mistake early on, picks one wrong token in that chain of logic, that error can cascade. It throws off all subsequent tokens, and the entire reasoning process can just fall apart. There's often no mechanism to go back and fix that early mistake.
That fragility. It explains why even these monster LLMs, the ones with trillions of parameters, struggle so badly with certain kinds of problems, right? Like hard logic puzzles.
Precisely. Things like Sudoku, complex mazes, or especially the visual reasoning challenges in the ARC-AGI benchmarks. These demand perfect logical consistency. One error, and the whole solution is wrong. The sequential, autoregressive nature just isn't well suited for that kind of zero-tolerance logic.
And the source material mentions some stats for ARC-AGI. Even state-of-the-art models struggle.
Yeah, it's pretty sobering. Even something like Google's Gemini 2.5 Pro apparently only gets around 4.9% accuracy on the harder ARC-AGI 2 benchmark. That's incredibly low for a frontier model.
Wow, okay. So how does the tiny recursive model, TRM, address this fundamental weakness?
TRM throws out the sequential generation idea, at least for the core reasoning part. It's a completely different philosophy. Instead of generating token by token, TRM focuses on iterative solution refinement.
Iterative refinement. Okay, what does that mean in practice?
Imagine you have a candidate answer, maybe the whole Sudoku grid. Instead of generating it cell by cell, TRM takes the entire candidate answer and tries to improve it all at once, based on some internal reasoning or error checking. Then it takes that improved answer and does it again and again, recursively getting better each time.
So it's more like proofreading and correcting a whole draft repeatedly rather than writing sentence by sentence.
That's a great analogy. Yeah. It's constantly looping back, refining the entire solution based on its internal thought process until hopefully it converges on the correct answer.
That's a really profound shift from the standard LLM approach. And the name, tiny recursive model. How tiny are we talking?
This is the really shocking part. The architecture is incredibly simple and small. It uses just a single tiny network, only 2 layers deep, and totaling just 7 million parameters.
7 million, not billion.
Million.
Yeah.
7 million parameters. For context, that's less than 0.1% of the size of even a small 7 billion parameter model.
Okay, that is genuinely tiny. How can a 7 million parameter network possibly perform complex reasoning?
The power doesn't come from the size of the network, the number of parameters. It comes from the depth of recursion. This tiny network recursively calls itself to improve 2 key things: the current predicted answer, which we can call A, and an internal latent reasoning feature. Let's call it 0.
Okay, Euler's is the answers, zeros is the reasoning. How does the recursive process work, step by step?
It can run for quite a few steps, up to not 16.6 refinement iterations in their experiments, which they call dump supervision. In each step, this little network essentially looks at the current state $6, the input problem $6, the current guess for the answer $, and the current internal reasoning state, 0.
Okay.
Then it does 2 things. First, it updates the internal reasoning of the $. It computes a new 0 based on the input 6, the old 0, and the old 0. Think of this as updating its internal thought process based on the current situation.
Right, refining the why.
Exactly. Then second, it updates the answer $. It computes a new answer $, based on this newly updated reasoning 0 and the old answer $. So the refined thought process directly informs the refinement of the actual solution.
And it just repeats that loop, update, reasoning, update, answer up to 16 times.
Potentially, yeah. This iterative looping allows the model to progressively identify and correct errors from previous steps. It's simulating a kind of deep, multi-step thinking process, but using this incredibly small, recursive computational core.
It's like it's giving itself time to think and rethink within that tiny structure.
That's a good way to put it. Now, if you've been following this line of research, you might know this TRM approach is actually an evolution, a simplification of an earlier model called the hierarchical reasoning model, or HRM.
HRM, right? I remember that one being quite complex mathematically. Didn't it involve trying to justify the training using something called the implicit function theorem, IFT?
Exactly. HRM was more complicated. You'd use 2 separate networks, had these kind of biologically inspired arguments, and yes, it relied heavily on the IFT to justify how it calculated gradients during training, especially for the recursive part.
What was the issue with using the IFT there? Why did TRM move away from it?
Well, the IFT is a powerful mathematical tool, but using it in this context required making a pretty strong assumption. It essentially assumes that during the forward pass, the recursive process settles down into a stable, fixed point, meaning the internal reasoning ZIVLMDA stops changing significantly after enough iterations.
It assumes the model reaches a perfectly stable thought before giving the final answer.
Right, and if that assumption holds, the IFT lets you calculate the gradients needed for backpropagation by only looking at the last 1 or 2 steps of the recursion, which is computationally cheaper.
Is that fixed point assumption actually valid for these complex tasks during training?
Probably not, or at least not reliably. That's what the TRM researchers found. Especially during the very dynamic process of training, the system likely doesn't reach a perfect fixed point. So that gradient approximation based on IFT becomes unreliable, potentially leading the training towards bad solutions or getting stuck.
So the mathematical shortcut wasn't quite cutting it in practice. How did TRM bypass the need for IFT then? Did they find a different shortcut?
Nope. They did the opposite of taking a shortcut. They just decided to pay the full computational price. Instead of approximating the gradient using IFT, they simply backpropagated the error signal through the entire chain of recursive steps, all $1 plus 1 recursions involved in that deep supervision step.
So they used full backpropagation through time, BPTT, just applied to this recursive structure. That sounds much more computationally expensive during training.
It is more expensive, definitely.
Yeah.
But the payoff was huge. By ditching the potentially flawed IFT approximation and just computing the true gradient through the full recursion, the model's ability to generalize to new, unseen problems improved dramatically.
How dramatic? Do they give numbers?
Yeah. On a benchmark called Sudoku Extreme, just switching from the IFT-based gradient approximation to full backpropagation through recursion boosted the accuracy from around 56.5%, what the older HRM-style models got, to a whopping 87.4% for TRM.
Wow, 56% to over 87%. just by calculating the gradient more accurately, even if it was more work.
It really shows that sometimes the straightforward engineering solution do the full calculation beats, trying to be too clever with mathematical approximations that might not hold true.
Okay, so they simplified the training math by making it more computationally direct. Did they simplify the architecture too, compared to HRM?
They did, significantly. HRM used two separate networks, often 4 layers each, and had more complex interactions. The TRM team experimented and found that using just a single, tiny 2-layer network actually gave the best generalization performance.
So fewer parameters, simpler structure was actually better.
Yes, it's a strong case of less is more for the network size itself. They hypothesized that larger networks, like the ones in HRM, were actually more prone to overfitting on the relatively small, specialized data sets used for these kinds of puzzle tasks, like ARC-AGI or Sudoku. There just aren't millions of unique training examples for those.
Interesting. So the tiny network size helps prevent overfitting to the training data, while the deep recursion provides the necessary computational depth for complex reasoning.
That seems to be the winning combination. And they also clarified the roles of those two recursive features, E and their dollars. They reinterpret simply as the current embedding of the solution candidate, and ZHLA is the latent chain of thought or reasoning feature used to guide the corrections.
And having both yell and dollars is important.
They found it was optimal. Trying to use only a single recursive feature or even multiple scales of latent features performed worse. The intuition is you need both the current answer to know what needs fixing and the reasoning trace to figure out how to fix it.
Okay, architecture simplified, training simplified by being more direct. Now for the results that really make you question the scaling paradigm, this 7 million parameter TRM going up against the behemoths on those hard puzzles.
The numbers are, frankly, stunning. On the ARC-AGI-1 benchmark, TRM hit 44.6% accuracy. On the harder ARC-AGI-2, it got 7.8%.
Okay, let's put those numbers in context again. You mentioned Gemini 2.5 Pro, estimated at over 1 trillion parameters.
Right. Gemini 2.5 Pro reportedly gets around 37.0% on ARC-AGI-1 and only 4.9% on ARC-AGI-2.
So the 7 million parameter TRM is beating a 1+ trillion parameter model on both benchmarks.
On these specific benchmarks, yes. And compared to something like DeepSeek R1, 671 billion parameters, which got about 15.8% on ARC-AGI-1, the TRM is way ahead there, too.
It's almost hard to process. A model using less than 0.01% of the parameters is achieving significantly better results on these complex, structured reasoning tasks.
It's a genuine shockwave. It fundamentally demonstrates that for certain types of problems, particularly those requiring precise, iterative, logical deduction, the architecture, how the model is designed to think, is vastly more important than just throwing trillions of parameters at it in a standard autoregressive structure.
It's like you said earlier, the tiny, perfectly designed tool outperforming the massive Dickerel purpose machine on a specialized job.
Exactly. TRM's iterative refinement is the right tool for deterministic logic puzzles. The LLM architecture, optimized for fluency and general knowledge, is simply the wrong tool for tasks where one logical slip invalidates everything. TRM proves architectural innovation can beat brute force scale, hands down, in the right domain.
Okay. We've gone through 3 really distinct and powerful paths now. We had the smart system design with agentic SLMs leveraging specialization. We had the smart training methodology with ProRL, pushing capability boundaries through intense learning. And now smart architecture with TRM, enabling deep recursive refinement. Let's try to synthesize this. What's the big picture message when you put all 3 together?
Well, the common thread running through all 3 is a direct empirical challenge to the old scaling is everything dogma. They collectively prove that innovation, real, clever innovation in system design and training techniques and in the fundamental architecture of the models can yield results that are superior to just making the model bigger. It shows capability is increasingly becoming a function of sophistication, not just size.
But the philosophies behind the 2 paths that really expand core capability, ProRL and TRM, they seem quite different, don't they? Even though they both empower small models. One feels like it's about exploring possibilities, the other about locking onto a single right answer.
That's a really key distinction, yeah. ProRL represents a philosophy of enhanced exploration and stochastic search. Its goal is to make a relatively small generalist model better at navigating a huge, open-ended solution space. Think generating novel code, finding creative solutions to math problems it hasn't seen before. It's about broadening the model's horizons, pushing the boundaries of what it can potentially do.
Okay, broadening horizons through exploration. And TRM.
TRM is the opposite philosophy almost. It's about specialized deterministic refinement. It's designed for highly constrained problems like these puzzles where there's typically one single verifiable correct answer. TRM doesn't explore broadly. It acts more like an optimizer, iteratively homing in, converging on that single correct solution within a very rigid set of rules or constraints. It excels at meticulous error correction in a structured way.
So one's an explorer, the other's a focused optimizer.
Exactly. And you can easily imagine how you'd want both kinds of intelligence in a really sophisticated future AI system, right?
Yeah.
You'd need ProRL style models for tackling complex, open-ended problems where creativity and novel approaches are needed. And you'd need TRM style specialists for tasks demanding absolute logical precision, iterative refinement, verification, or optimization within known constraints.
That makes sense. You deploy different types of specialized SLM intelligence depending on the nature of the task. Which brings us nicely to the practical side of things. The research doesn't just present these concepts, it actually outlines a kind of roadmap for businesses, right? A way to transition from using one big LLM to using these specialized SLM agents.
Yes, they lay out a pretty systematic process, an LLM to SLM conversion path, designed for getting this stuff into production relatively quickly.
Okay, what are the steps? Where do you start?
Step 1 is the absolute foundation, secure usage data logging. If a company is currently using a big LLM for various automated tasks, not just direct human chat, they need to meticulously log everything about those agent interactions. The input prompts, the LLM's responses, any tools or APIs the LLM called, and crucially, some measure of how successful or useful the response was. This log data is the raw material for building specialists.
Got it. Log everything the agent does. Step 2.
Data curation and filtering. This is partly standard stuff, removing personally identifiable information, PII, maybe obfuscating other sensitive company data. But the research also suggests using tools, maybe even another AI, to automatically paraphrase some of the domain-specific inputs.
Paraphrase, why not just use the raw anonymized logs?
The idea is to make the training data more generalizable. You want the SLM specialist to learn the underlying task pattern like extract invoice number and total amount without overfitting to the specific phrasing or named entities in the original logs. Paraphrasing can help create more varied examples of the same core task.
Okay, clean and generalize the data. What's step 3?
This is where the specialization starts to emerge. Task clustering. You need to figure out what specialized SLMs you actually need to build.
So you analyze the logs to find recurring types of requests.
Exactly. You use unsupervised machine learning, clustering algorithms to sift through all those curated logs and identify distinct recurring patterns of agent activity. Maybe you find one cluster is all about summarizing customer support tickets, another is generating SQL queries from natural language, another is classifying product defect reports. These clusters define the domains for your future SLM specialists.
Right. Identify the jobs that need doing repeatedly. Then step 4 must be building the specialists.
Precisely. SLM selection and fine-tuning. For each cluster you identified, you first choose an appropriate base SLM, maybe a good open-source 3B or 7B model that has decent general capabilities relevant to the task. Then you fine-tune that base SLM specifically on the dataset created from that task cluster.
Using those efficient techniques like LoRa or QLoRa we talked about earlier.
Exactly. PEFT methods make this fine-tuning step fast and cheap. This is also where you might use knowledge distillation.
Distillation? You mean training the small model to copy the output of the big, expensive LLM?
Yeah. You use the high-quality responses generated by the original LLM from your logs as training targets for the small model. This effectively transfers some of the sophisticated knowledge or stylistic capabilities of the large model into the much smaller, more efficient specialist SLM.
Okay, so you create these tailored specialists. Is that the end of the process?
Not quite. The final ongoing step is iteration and refinement. The world changes, user needs evolve, data formats get updated. So these specialized SLMs need to be periodically retrained or further fine-tuned with new usage data to keep their performance high and ensure they adapt. It's a continuous improvement loop, but one that's feasible because the SLMs are small and cheap to retrain.
It sounds like a very practical pathway for companies to start leveraging these SLM efficiencies without having to completely ditch their existing LLM investments right away.
Exactly. It's an evolutionary path towards a more efficient heterogeneous system.
Looking at the bigger picture then, beyond individual companies, what are the macro implications of this whole shift towards smaller, smarter models?
I think the implications are pretty profound, especially for democratization and sustainability in AI.
Democratization?
Yeah.
Because it lowers the barrier to entry.
Massively. For years, cutting-edge AI development felt like it was concentrating in the hands of just a few giant tech companies, the ones with the billions needed for massive compute clusters to train ever larger models.
Right, the compute haves and have-nots.
This move towards highly capable small models changes that dynamic.
Yeah.
Suddenly, smaller research labs, universities, startups, even individual researchers, they can realistically develop, train, and deploy genuinely powerful and sophisticated AI systems without needing access to a hyperscaler's budget. It opens up the field for much broader innovation.
And the sustainability angle. Smaller models mean less energy.
Significantly less energy, both for training and especially for inference at scale. Lower compute needs, lower energy consumption. It just makes deploying AI more environmentally sustainable. Plus, the ability to run these models on edge devices makes powerful AI accessible in places or situations where relying on a massive cloud connection just isn't feasible. It makes AI more flexible, more resilient.
It really does feel like a pivotal moment, doesn't it? Shifting the focus from just raw size and budget towards ingenuity, towards cleverness and design and training. The goal isn't just capability anymore, it's capability achieved efficiently.
Couldn't agree more. We've covered a lot in this deep dive, exploring this fundamental shift away from bigger is always better. We looked at the three main paths driving this: smart systems using agentic SLMs for distributed intelligence, smart training like ProRL unlocking new capabilities through intense prolonged learning, and smart architecture like TRM enabling deep, iterative reasoning in tiny packages.
And the underlying message that comes through from all three is crystal clear. The frontier of AI is expanding, yes, but not just in sheer scale. It's expanding in sophistication, in cleverness. Finding smarter ways to design, train, and deploy models is proving to be a more effective, more sustainable route to genuine power than just brute force.
So maybe we can leave our listeners with a final provocative thought to mull over.
Go for it.
Considering the absolutely mind-bending gains we saw from that tiny 7 million parameter TRM on those ARC-AGI puzzles problems that totally stump trillion parameter giants, it forces you to wonder, what other fundamental tasks are out there, tasks that we currently assume require massive scale, maybe even tasks we haven't managed to crack at all yet? Could they actually be solvable with tiny micromodels if only we find the right architectural trick, the right training insight, the right recursive loop?
Finding that right trick for problems we think need brute force today.
The answer to that question? Well, it could very well define the entire next decade of progress in artificial intelligence.